Over the last decade, India's space agency has perfected the art of landing robotic rovers on the moon. Now, ISRO is targeting a crewed moon landing by 2040 and building an independent space station along the way. But there is a massive physical barrier standing in their way. This is the LVM-3 rocket on the launch pad at Sriharikota. It's India's heaviest launch vehicle, but it simply lacks the payload capacity to lift deep space return missions or heavy human habitats in a single go. Waiting decades to design and build a larger rocket would stall their timeline, so ISRO is splitting their entire space program into two parallel tracks to bypass this weight limit entirely. They are treating orbital mechanics as an architectural problem, innovating through modular workarounds rather than relying on brute force rocketry. Track 1 is all about moving heavy hardware. The upcoming Chandrayaan 4 mission aims to dig up lunar surface samples and fly them back to Earth. This diagram shows the problem. A complete sample return requires a lander, an ascent vehicle, and a return capsule. Stack all 4 modules together, and the combined weight is far too heavy for a single LVM-3 launch. To solve this, ISRO will divide the payloads. They will launch the modules separately on 2 different rockets, one heavy-lift LVM-3 and one workhorse PSLV, sending both into low Earth orbit. Once in orbit, a technology called the Space Docking Experiment, or SPADX, takes over. The 2 separate modules will autonomously align, dock, and physically connect to form one massive spacecraft before firing their thrusters toward the moon. This same assembly logic will scale up for Chandrayaan 5, allowing India and Japan to jointly deliver a massive 250-kilogram robotic rover to the lunar surface. By mastering in-space docking, ISRO has essentially eliminated the payload limits of their launch vehicles. They have turned Earth's orbit into a construction site. Track 2 is the ambitious Gaganyaan program. This is the orange crew module prototype, representing the complex challenge of engineering an ecosystem that can keep humans alive in the vacuum of space. To pull this off, engineers have to upgrade the LVM-3 to meet strict human rating safety standards while simultaneously developing indigenous spacesuits and high-speed emergency abort systems. Before putting a human inside, ISRO is running uncrewed safety test flights. Here you can see Vyomitra, a highly advanced humanoid robot packed with specialized sensors that will gather biological and acceleration data in place of live animals. ISRO is also taking a strategic shortcut to gain immediate operational experience. Look at this patch for the Axiom 4 mission. Through a partnership with NASA and SpaceX, an Indian astronaut will fly aboard a Crew Dragon to the International Space Station. This ISS mission acts as the final knowledge bridge before India launches its own indigenous crewed Gaganyaan 4 mission, currently slated for 2027. The Gaganyaan track requires massive investments in testing and materials to build the foundational infrastructure of a permanent, sovereign human spaceflight program. When these 2 development tracks finally converge, the mission goals translate into a single, comprehensive capability. Track 1 provides the heavy modular assembly. Track 2 provides the biological survival systems. The result is the Bhartiya Antariksha Station, a 52-ton orbital habitat assembling itself piece by piece above the Earth. This station will act as the ultimate staging ground, relying entirely on the autonomous docking technology proven by Chandrayaan, and the advanced crew habitats perfected by Gaganyaan. These upcoming launches are not isolated science experiments. Every mission is a specific technical prerequisite for the next, scaling up toward the completion of a permanent, multi-modular orbital outpost. In 1984, the first Indian citizen traveled to space. But as these framed photos in the background show, that milestone relied entirely on Soviet rockets, Soviet capsules, and Soviet hardware. Now look at this sprawling modern mission control center. Within the next decade, the engineers in this room will command India's own modular space stations and lunar return vehicles with absolute technological sovereignty. India has moved beyond its historical role as a low-cost carrier for foreign satellites. By solving the heavy lift bottleneck through modular design, they have secured the ability to build and sustain their own deep space infrastructure. The 2040 target for an Indian astronaut on the Moon is supported by an active, funded engineering pipeline. For ISRO, the countdown is already underway.